We are at the network layer looking at the internet protocol. A few questions first. There's a lot of action at this layer, some rather straightforward, some very interesting. So we will cover all this functionality over the course of many videos. In this video, we will focus on some straightforward stuff, that of packet format and fragmentation and reassembly. So here is the IP packet format arranged in 32-bit blocks. So it begins with the version field, which specifies the version of the protocol. So we are in the process of transitioning from IP version 4 to IP version 6. We will cover IPv6 later, but henceforth we will focus on IP version 4. Why do you think this IP version appears at the very beginning of the header? Is there any reason for this, or it's just like that it has to appear someplace? Well, how you interpret the remaining fields is a function of which version of IP protocol you are following. So once you know the version, then you can interpret all these other fields. So it has to come at the very beginning. So following version is the HL field, which stands for header length. So this specifies the entire IP header in 32-bit words. So for example, if HL takes on a value of 5, that means the header length is 5 into 32, that is equal to 160 bits. But why do we need to specify this header length? This is arising because of this field options, which can be variable. Thereby you need to specify how long the header goes. Following header length is the type of service field. So what is the service that IP layer offers? Best effort service, no guarantees of any kind. But when people designed the IP protocol, they provided this field in case you want to treat packets differently. For example, if there is an audio packet, you can indicate that this is an audio packet by specifying some number as part of the type of service, which shows that this is an audio packet. And then that packet, because it needs some delay guarantees, you can potentially service it ahead of others. But this has mostly been of research focus, where the definition of type of service has varied over the years. Very few routers implement this aspect. It has not seen much widespread use. So following this is the total length field, which specifies the entire length of the datagram, including the header, in bytes. Note, this is not in 32-bit words, but in bytes. Then come the fields identification flags and fragment offset. This is to help in the fragmentation and reassembly that I mentioned earlier. But first, tell me, what is the maximum size an IP packet can take? So since the total length field is 16 bits, you can have 2 to the power of 16 minus 1 bytes, because this total length captures the byte count. So you saw in case of Ethernet that Ethernet can only take 1500 bytes as the payload in the frame, whereas the maximum size of the IP packet can be much larger than this. Typically, different physical networks will support different packet sizes. So if you have a big packet and your underlying physical network does not support it, you need to fragment that particular packet and reassemble this. We will cover more of this in the later portion of the video. Next comes the time to live field. We saw in the spanning tree protocol that when you build networks, some loops creep into the network topology, either because of fault tolerance purposes or misconfiguration. And whenever we have loops, you will see that the packets are going to go round and round. How do you help catch such packets? If you went with the name, you could have thought, let me give an expiry date for each packet, let's say X seconds. So if the packet is still in the network past the expiry time, just drop the particular packet. Great, but what functionality will the routers need to implement this particular feature where they can detect that this particular packet is past its expiry date? So the routers need to be time synchronized, which is not easy to achieve in practice. So what this field typically has boiled down to is a hop count. So basically you start out with a default value here. Whenever the source generates this particular datagram, it sets the time to live equal to 64. The hope here is that the number of hops between the source to destination will always be less than 64 hops. So if it is taking more than 64 hops, that means it is doing rounds. So let's drop this particular packet. So the routers, whenever they receive this packet, they are going to decrement the field by 1 before forwarding. And if a router receives a particular datagram with this field equal to 0, that means that time has expired, or in this case the hop count is expired, just discard it. Next is the protocol field, which you must be familiar with from before. So this is the demultiplexing key that identifies the higher layer protocol. So if you want this payload, the data, to pass to TCP, you set this value equal to 6. If you want to pass it to UDP, you set it equal to 17. Then comes again another field which you are familiar with, which is the internet checksum. So this checksum is calculated only over the header. Why do you think that is? So when we talked about router design, we mentioned about the switching speeds, how a packet should spend the least amount of time in a router before getting out of the router. So if this checksum field is calculated only over the header, the router can quickly process the packet and get it out. The main characters in the packet format are the source and destination addresses. So these are 32 bits each. Without a destination address, there is no forwarding. So destination is the key to forwarding. So you also include the source address so that the destination can reply back to the source. So these addresses are unique, much like the addresses at the link layer, the MAC addresses that we have seen, and these are also independent of the physical network address. We will spend a considerable amount of time on addressing later. Following the addresses are the options field. These are rarely used in practice, but they are there in case you need them. So options can be used, for example, to record the timestamp. So as a packet goes through each router can timestamp saying I received this packet at this particular time. This can help in performance calculations, like how much time a packet spent at each router, what was the round trip time, so on and so forth. You could also record the route taken by a packet. I remember I mentioned that you can support source routing as part of datagram networks. So you can specify the source route as part of options, in which case the routers will use this route to forward the particular packet. Following this is the payload or the data. This is typically higher layer data, either TCP or UDP-SIG.